Greetings, awesome physics students. I wanted to do another example statics problem. So recall in statics, the objects are in equilibrium. So the sum of the torques is 0 and the sum of the forces is 0. And this is a two-dimensional statics problem. So let's go ahead and get started. The question is, we have a uniform beam of length 1 meter here, and it's attached to the wall. And where it's attached at this point right here is it's free to pivot about that point. And there's also a cable attached here that at the end at an angle of 30 degrees to the beam. So we want to find the tension in the cable. So to start this problem, we want to first start by, well, we have a picture of it. We want to draw the free body diagram. We want to draw the free body diagram for the beam only. Okay, so let me let's draw this down here so we have a little room. And we have the tension, of course, on this. We also have, we're given that it has a mass of 20 kilograms. So there's a weight associated with that mass, the force of gravity, and that's going to act at the center of mass. So that's going to be in the middle of the beam because it's a uniform beam. So that's going to be mg. And because of that, force down, we're also going to get a support force at the end here. Now this force, where it's free to pivot, that means it's not going to exert any kind of torque on it, but it will exert an X force because something has to oppose the tension force, the X component of the tension force, and then it probably has a support force there too. Right, and I'm drawing these forces on here a little different than I usually do. You can draw them emanating from the center where they act like we did with gravity and tension, or you can draw them pushing, appearing to push on that point. That's fine. Okay, so let's go ahead and get that. Once we have our free body diagram, then we want to look at establishing a coordinate system. So let's just use a standard coordinate system, and we'll use counterclockwise as positive when we do the torques. And then we want to go ahead and sum the torques and sum the torques about any point. And we also want to sum the forces in the X and Y direction. And those are going to be 0 because there's no acceleration, no angular acceleration and no linear acceleration. We could start with summing the forces. I think that's fairly straightforward, but we have 4 forces here. And so we're not going to get a clear resolution with just the sum of the forces in the X and Y direction. I think instead what we need to do is sum the torques. So let's start by summing the torques. And whenever you sum the torques, you always have to choose an axis to sum them about. So in this case, in statics, we can use any axis because there's no angular acceleration about any axis. It's wise to choose that point to be a point where there are forces acting that you don't know about and you don't care about. And I think that would be this point right here. We don't know those support forces, and we also don't care about those support forces. We're not asked about them. So let's choose that point. We'll choose the pivot as our axis, and we'll sum the torques about that point. So we're going to have, so let's just go force by force. We're of course going to have this X force here, from the pivot. So let's just call this the force from the pivot in the X direction. This is going to be the force from the pivot in the Y direction. And those are going to produce 0 torque because remember the R vector, the R vector goes from the axis of rotation that we're considering to the point where the force acts. Well, both of those are in the same point. So R is 0 for both of those. Okay, so I'm going to get 2 terms there of 0. And then the next force we have is mg. And the R vector for that one is going to point from the axis to where that force points. That's going to be half a meter because the entire thing is 1 meter and the center of mass is in the middle. So that's going to be 0.5 meters. times mg, that's going to be 20 kilograms times g, 9.8 newtons per kilogram. And that one causes rotation around the pivot point in a clockwise fashion. Hope you can see that. And so that is going to be a negative torque. So I have to put the negative sign in there by hand. Let me just move that negative down here. Okay. So that force is done. Now, last we have our tension force, and that's going to be, there's going to be a torque from the tension force. In that case, the R vector is the entire 1 meter. And so that's going to be 1 meter times the tension force, which we don't know. And we only want the vertical part of the tension force. Okay, so we want to use, this angle is 30 degrees. That vertical part of the tension force is also going to be this part. Notice that's opposite of the angle 30 degrees. So we're going to use the sine of 30 degrees there to pick off the perpendicular part of the tension force, the part of the tension force that's perpendicular to our R vector. Alternatively, you could just take the distance, the R vector, times the force vector times the sine of the angle between them. And that works too, okay? This tension force is going to cause counterclockwise rotation around our pivot point here. So that one is going to be a positive torque, okay? And now I have identified a torque with each one of these forces here. 4 forces, 4 torques. I have 4 terms, 1, 2, 3, 4. And so I'm done. And so I set these torques equal to, the sum of these torques equal to 0. And now I have one equation and one unknown. I hope you can see that if I had instead summed the forces in the x direction, I would get the force from the pivot in the x direction minus the tension force times cosine of 30. That gives me 2 unknowns in one equation. That's not good. And if I'd sum the forces in the y direction, I would get the force from the pivot in the y direction plus the tension force in the y direction minus mg. And again, that gives me 2 unknowns and another equation. So if I'd started with the familiar summing the forces, I would have 4 unknowns, but only 2 equations. So that's not good at all. Whereas the torque equation gives us 1 equation, 1 unknown. It's beautiful. Now it may be a little less comfortable for you in the beginning, but I would highly encourage you to start by summing the torques about a strategic point here, like we did. Okay, so let's go ahead and solve this 1 equation and 1 unknown. I get 1.0 meter times, I'm going to write this term out, times ft sine 30 equals, and I'm going to throw this on the other side here, and that's going to give me 0.5 times 20 kilograms times 9.8 newtons per kilogram. And then I divide both sides. The tension, I'm going to divide both sides by these 2. And so that gives me 0.5 meters times 20 kilograms times 9.8 newtons per kilogram. Sorry for my bad handwriting here. 1 meter sine 30. And I can go ahead and compute this and get a number here. So when you type this into your calculator, then you get 196 newtons. Notice that I know it's newtons because the meters here cancels the meters here. And then I have kilograms. The kilograms here cancels the kilograms here. And I'm left with newtons. And sine 30 has no units. So that's how the units shake out. Okay, so the correct answer here is 196 newtons. Hopefully you can see the relevant parts here is that we actually only needed to sum the torques about a certain one strategic point, and that was the pivot point right here. And recall we did that because we had 2 forces there that we didn't know about and we didn't care about. And whenever you have static equilibrium like this, the sum of the torques about any axis is going to be 0. So you can use any axis, you can choose your axis the way you like. And we chose it wisely there to give us one equation and one unknown. All right. Hopefully this was helpful. And if you have any questions, as usual, please let me know. See you later. Bye.